Yeah, hello and welcome everyone to the 19th lecture of our CUDA program. So in the previous lecture, we saw things related to the support, right? Support aspects of the CUDA programming. So we saw how to write the make files. We saw what are rules, what are targets, what are prerequisites, and what are the commands associated with the make file. And then we saw multiple examples related to the make file. We saw how to use variables, if conditions, and for and while loops inside the makefile, and then at the end we saw uh, one complete example for running a CUDA program on multiple test cases using a makefile. And then we saw debugging aspects uh, of the CUDA programming. So we saw how to use CUDA GDB to debug our CUDA programs. And later we touched briefly upon the profiling aspects, that is how to time our CUDA program, that is how to know how much time our kernels are taking for running, and which will help us in determining which kernel to optimize and so on. So that the information we can get using either NVProf or NVSite, and we saw NVProf specifically in the previous lecture. So yeah, that is where we ended off in the previous lecture. And yeah, that is the outline. That was the outline for the previous lecture. For today's lecture, we are planning to cover three specific things. One is dynamic parallelism. That is, so that is when we are calling kernel from within another kernel. That is what is called as dynamic parallelism. So we'll see how to do that. We'll see problems related to it, and we'll briefly touch upon the computation and the memory aspects of the dynamic parallelism. And then we'll start off with the multi-GPU processing. That is, when we have multiple GPUs associated with our CPU, how to program them. First of all, we'll see why do we need multi-GPU processing, and then we'll also see how to do multi-GPU program using multiple APIs and functions that are available in CUDA. And yeah, that is what we'll see in multi-GPU processing. And then we'll towards the end we'll see this warp voting. That is, what is warp voting and what are the multiple functions that are available for performing this warp voting, and we'll see all these things towards the end of the today's lecture. So okay, with this let us start, but before, let me see if there is anything in chat. Okay, recording has started and there is nothing in the chat. Okay, fine. So yeah, so let us start with the today's content. Okay, so yeah, let us start with this first subtopic, that is dynamic parallelism. So this dynamic parallelism is typically useful in the scenario where we have nested parallelism. That is, we are launching a kernel with n threads from the CPU. That we know, right? We can launch a kernel from CPU with n threads, and then that each thread of that kernel will be launching again another kernel with n threads. So I hope we are understanding that there are n threads, where each thread is again launching a kernel with n threads. So in total we have n into n, that is n square threads that are running on the GPU. And this dynamic parallelism can be useful for modeling such kind of nested parallelism scenario, which I told that, like there are n threads, and each thread is again launching n other threads for doing some nested kind of operations. So let us come to this example, that is nested for loops, and we'll see if this nested for loop can easily be modeled using dynamic parallelism. So yeah, we have this outer for loop which is running for some constant number of iterations. Let us say that there are n iterations of the outer loop. So outer loop is running from 0 to n, and then again inner loop is running from some fi, that is some function of I, and please note that this I is the outer loop. So this value of fi is known at runtime, so it is running from fi to n. So outer loop is running from 0 to n, and for each iteration of outer loop, this inner loop, which is this j, is running from fi to n. So the number of iterations in the inner loop are vary based on this function fi. So to model such kind of scenarios, we can use dynamic parallelism. So what we can do is we can launch a kernel from the CPU with n threads, which can model the outer loop. That is, this outer loop was running for n iterations, right? So for one particular iteration, we can have one thread. So we can launch the kernel from CPU with n threads. That will be suffice for the outer loop. But for the inner loop, what we can do is from that kernel which has which is being ran by n threads, we can launch another kernel which will run for n minus fi number of which will be launched with n minus fi number of threads. So I hope you are getting it. This inner loop is running from fi to n, so the number of iterations that it will have is n minus fi. So we are launching a kernel from CPU with n threads, and each thread of that kernel will launch again another kernel with n minus fi threads, and that kind of a launch and execution pattern can easily model our can efficiently model our this kind of nested for loops. And yeah, we can then place this whatever work we are doing in that kernel. Yeah, so we will see this with an example, but yeah, so the important point to observe here is that there is this fi, right, this function whose value is known at runtime. So whenever we have this inner loop whose iterations are not known until the runtime, we can use dynamic parallelism. We should use dynamic parallelism. But for the case where we already know the values of not values, but we already know the number of iterations for which the inner loop and outer loop are running. For let's say, for example, that we already know that inner loop is running from 0 to n, and outer loop is running from 0 to n, and inner loop is also running from 0 to n. In that case, what we can do is, instead of just using dynamic parallelism, well, we can use dynamic parallelism, but instead of using dynamic parallelism, what we can do is we can just unroll the loop and can do this work. Do this work with the help of just single kernel. How we can do that? We can just launch that kernel with n into n threads, that is n squared threads, and do that computation, this work inside that single kernel, instead of using dynamic parallelism, that is launching the kernel from within a kernel. We can use just single kernel and launch it with n squared threads. But yeah, when there is such kind of scenario that there is outer loop and inner loop, iterations of inner loop are dependent upon the outer loop, we need to use dynamic parallelism, because it eases it eases down the modeling of such kind of scenarios. So I hope that is clear. Okay, so typical examples of dynamic parallelism are the algorithms where we have hierarchical data structures. That is, let us assume this scenario that we have a tree, and each node of a tree can have it can have a variable number of childs. So the nodes that a particular the number of childs that a particular node have depends upon the type of node it is. So in that case, it is this kind of scenario, right? Let's say we are looping over the outer loop, that is all the nodes of the tree, and based upon the whatever node it is, we are going through all of its child, that is f of I. So consider f as a neighbor function. So we are going through, or the child function. So we are going through all the child of a particular node, which is I. So in that case, since the number of nodes that each child can have might vary, so in that case, probably we can use this dynamic parallelism to model this kind of algorithms where there are hierarchical data structures. So this is one of the examples. Then there is this example of the algorithms where we use recursion. So if you people know, then we can model recursion using something called as recursion tree, and the number of calls that a particular node of that recursion tree might make might vary, right? So yeah, since that number of calls at a particular node in recursion tree that might the node of that recursion tree might vary, again it comes it boils down to this kind of processing, right, where number of iterations of the inner loop are not fixed, and hence again it can be modeled using something called as dynamic parallelism. And then again there is another example that we have work that can naturally split into the independent batches, and each batch can be processed parallelly, as well as the amount of work in each batch is not uniform. That is, each batch doesn't have the same amount of work to do. In that case, again, the amount of work is not fixed. So it is again like this, that the variable amount of work is being done. That is, the inner iteration, the number of iterations of the inner loop is not fixed. That is, the amount of work that is to be done by that is to be done by a particular batch is not fixed. Hence, again, we can use dynamic parallelism to model this kind of scenarios. And so again, I will repeat this point that not all the nested parallel loops needs dynamic parallelism. That is, if we know the number of iterations of the loops, that is, if we know the number of iterations of the inner loop and outer loop, then in that case, instead of using dynamic parallelism, what we can use is we can just unroll these loops and we can use static parallelism. That is, what we can do is we can just launch one single kernel with n square threads instead of launching launching a kernel with n threads and calling again a kernel with n threads from each of that thread. So I hope that is clear. So for where the loop bounds are already known to us, we can use static parallelism. But where the number of iterations for a loop is not it cannot be determined during compile time, we should use dynamic parallelism. And these three examples are for the scenarios where we should use dynamic parallelism. And yeah, I hope this is clear. If there are any questions on this slide related to this dynamic parallelism, please let me know. Okay, I think there are no questions. Okay, in that case, let us move further. So yeah, let us start with one very simple example related to the dynamic parallelism. So we have this main function. In this main function, we are calling this kernel parent, and this parent is being launched with 3 threads. And yeah, all these three threads are from this same work, and then we are doing CUDA device synchronize. And within this parent kernel, what we are doing is we are printing the ID of that thread, and then again we are launching the kernel from within a kernel. Please note that this parent is a kernel. Please note that it is marked with global, and we are printing the ID of that thread in that kernel, and then again we are launching a kernel which is named as child with 5 threads. So I hope you are getting it. This code will be run by 3 threads independently, and this kernel, which is child, will be launched by 3 threads. And in that we are passing the thread ID, that is ID of that particular thread. And yeah, what is this child kernel? Let us come to it. So this child kernel is again kernel because it's marked as global, and it is taking some argument, which is the ID of the thread with which ID of the thread who has invoked it, that is its father. And what we are doing is we are printing the parent thread, that is its father, and the child thread ID. So parent thread ID and child thread ID we are printing. So yeah, this is a typical example of the dynamic parallelism, because if you see, we are invoking a kernel from within a kernel. So parent is a kernel, and from that we are calling some another kernel which is child. So let us see how to run this program. So I ran this program using NVCC dynamic par.cu. So this file name was let's say dynpr.cu. So I ran this kernel with this NVCC dynamic par.cu, which is the name of the file, and it gave me error. That is, calling a global function from a global function is not allowed on the compute capability on the compute_35 architecture or above. Is only allowed on the compute 35 architecture or above. Okay, so it is saying me that you can only use dynamic parallelism if you have compute capability of 3.5 or higher. So that is not a big deal. We can just specify it using the flag, which is ARCH. So we can specify that the compute capability that I'm using is SM_35. So I specify that, and then again rerun it. But again it gives some error to me. What is what it is trying to tell to me is that kernel launch from device or global function, that is, we are launching a kernel from device or a global function, requires separate compilation mode. So it is trying to indicate me something, that you need to use some separate compilation mode. And why it is telling to me this, why it is saying this, is that this child kernel that we are calling from the parent kernel needs to be linked with this this parent kernel, and for doing that we need to specify another flag, which is RDC, and this RDC will make sure that linking of the child kernel will happen with the parent kernel. And yeah, this for that we need to set this RDC flag to true, and RDC stands for, I think, relocatable device code or something. So when you set RDC flag to true, and when you compile it, if using, if you use both of this flag, that is arch is equals to SM35 and RDC equals to true, and then you pass this file name, then it will compile properly, and then you can run /a.out. Okay, so this is fine. So yeah, this file can be, it will be compiled and run properly. And okay, so next question is, what will be the output of this program? Considering that we have this program written and we are compiling and running it using these commands, what will be the output of this program? I request each and every one of you to try that. What will be the output of this program? Please try out and paste your answers in the chat. I'll wait here for a few seconds. Let me see if there is some. Okay, so there are some overheads associated with the dynamic parallelism. So I think Gokul's question is there any downfall to dynamic parallelism, or is it okay to use it when static parallelism is enough? Yeah, so there are some downfalls to the dynamic parallelism. First downfall is that it has this kernel call overhead itself, right? When we try to call a kernel from within a kernel, there is a kernel call. Kernels are called from within a kernel, and since we are invoking large number of kernels right now, there is this kernel call overhead associated with each launch, and that will definitely slow down our processing, and we should be careful about that. That is one point. And there is another point related to memory that we'll see later in this lecture. And yeah, in general, my observation is that if you can do some, if a work or a particular task can be accomplished with static parallelism, then you should not go for dynamic parallelism, since it has some overhead and some cost involved with it. Otherwise, if it's inevitable, like for the cases where we saw, right, that the amount of computation that we want to do is not fixed in some in some loop, then in that case we have to use the dynamic parallelism, and for that we can go for it. But that is fine since we have no other alternative. But for the case where static parallelism is available and we can use that, we should go for it first, is what my suggestion is. I hope that was clear, Gokul. Okay, I think yes. There is some response. Sorry, parent 0, child 0, parent 0, child 1. Okay. Any other response apart from this? Okay, I'll switch back to the slide so you people can try. Again, so I reiterate my question. What will be the output of this program? Please note that there are two print statements here. First is inside the parent kernel, and another one is inside the child kernel. So please think about it. I'll wait here for a few more seconds so that you people can try out, and I'll keep this slide as it is so that you can see the code. And yeah, I'll wait here for a few seconds.
Sir, I had a doubt there.
Yeah.
Sir, don't we need a CUDA malloc for passing that thread idx.x there in int father? Like, don't we need to declare it as CUDA by using CUDA malloc that father?
Okay. I think this is a good question, but let us pick this up. So what he's suggesting is, why don't we? Should we do CUDA malloc for passing this thread idx.x? Here we don't need it because let us understand why we don't need it. So whenever you declare this variable int father here, it is local for each thread, and since it's a local variable, each thread has its own private copy, and hence we don't need to do CUDA malloc. If you want some common variable across all the threads for the launched kernel, which is here, which is child, you need to do CUDA malloc. But for a thread local variable, that is no need of CUDA malloc. Think of it like this: we were having, right? We were passing that. What I can say, we are passing some information to the kernel from the CPU, right, using some parameters. For that, we weren't doing any CUDA malloc unless it was an array. Unless it was an array, we were just passing it using some like this. I mean, using some variable. So for that, we don't need CUDA malloc.
Yes, I got it.
And yeah, one more point that I want to clarify is this father, which is here, will only be, I mean, it's a thread local variable, so its value will only be visible to the particular thread. Okay, I hope that you are getting it, that it's a thread, I mean, thread local variable, so each thread will have its own copy. Well, we are not here modifying that variable father, but please note that it's a thread local variable, and hence, yeah, so yeah, I'll leave there. So each thread will have its local copy. So let me go back to, sorry. Okay, so there is some Gokul is suggesting parent 0, then it will print parent 0, child 0, parent 0, child 1. Okay, I think this looks correct to me. Okay, let us see with this code, along this code. So okay, this output would be like somewhat it will be like this. So let us understand why we are getting this output. So okay, let us understand step by step. So here CPU will launch the kernel with 3 threads, and then CPU will wait here at CDS, right? And then what is happening at this in this parent kernel? So since these 3 threads are the warp threads, they'll execute this print statement. So they'll print do this printf, and only they'll move to this kernel launch. And so first of all, they'll print this parent and then particular thread ID. So so this thing will be printed: parent of 0, parent 1, and parent 2. And since these 3 threads are the warp threads, they'll finish this statement, and then only they'll move to the kernel launch instruction here. So this will be printed, and then each of these 3 threads will launch their child kernels. So 3 child kernels will be launched, each with 5 threads. And what this child kernels will do, they'll print this statement. That is, there are 5 threads. Each thread will print what is its parent and what is its ID. So since there are 5 threads, we'll have this 5 statements for each and every parent. I mean, for each and every parent, right? So this kernel child was being launched by 3 threads, and this each 3 launch were having 5 threads. So this is for the first thread, first launch. This is for the second launch, and this is for the third launch. So I hope you are getting it. That the thread 0 within the parent is printing this first blue set of statements. Then the thread 1 of this parent kernel is printing this maroon set of statement, and then this thread 3 of the parent is printing this black set of statements. And since we have 5 threads for each call to child here, we'll have these 5 statements being printed. That is child 0, child 1, child 2, child 3, child 4. So I hope you are getting this parent 0, and then child 0, parent 0, and then child 1, and so on till child 4, and then again for parent 1, and then for parent 2. So I hope that this is clear. Any questions up till this point? It is important to understand this thing. So please feel free to ask any questions if you have. Any questions on this slide? Okay, I am assuming that okay, if there are no questions, let us move further. Okay, so I would like to ask you one question here. Can it happen that this maroon set of statements which are printed by the thread with thread ID 1 of this parent call are being printed before this blue set of statements? So my question is, like, can this maroon set of statements come before this blue set of statements here? So this will come here and this will go down. Can this happen? Is what my question is. Is it possible, or it will never happen? Please think about it. I'll wait here for a few seconds so that you people can think. Okay. Gokul is saying that it is possible. Any other suggestions? Okay, let us go back to the slide. So yes, this is possible because since each thread, so okay, so let us understand this. So warp threads were doing this print statement. So these three things were printed. Now warp threads, which were having ID from 0 to 3, they launched the kernel, and this launch can be arbitrary. So thread, they'll launch the kernel, here, and then it might happen that print buffer, the things, the output that was printed by the parent one, uh, the buffer in which the output was being dumped by the parent one came first to the uh, to the caller, and it was being printed first. So that can definitely happen. So this entire maroon set of statements can precede the blue set of statements, because printing can happen in arbitrary order, right? Since this calling is happening by all the three threads simultaneously, the printing can happen also simultaneously, and they can be jumbled in arbitrary manner. So even it can happen that this parent 2 is printed before all this parent 0 and parent 1 on all this blue and maroon statements. So that is definitely possible, because three threads are calling the kernel simultaneously, and they are being executed. They'll print at the they'll run concurrently this print statement. So that is definitely possible. So I hope that is clear. But what cannot happen is that this printing of this parent 0, child 0, parent 0, child 1, and child 2, child 3, child 4, that is this 5 set of statement for each and every parent, they can't jumble because they are warp threads, and the way printing of the warp threads is being done is that they'll be placed in the buffer one after the another. So parent 0, child 0, parent 0, child 1, parent 0, child 2, and so on till parent 0, child 4 of each of this parent 1, parent 2, and parent 3, they cannot jumble. Yeah, so I hope you are getting this, that internal jumbling is not possible, but across parents there can be a jumbling. So yeah, any questions up till this point? So there is some question. Child is called at same time by warp thread, so I assume there will be 3 instances of child. The child is called at same time by warp threads. Yes, that is correct. So I assume there will be 3 instances. Yeah, that is correct. Yeah. So I think this is correct observation. Okay. So let us move ahead. Okay. So let us examine what will be the output of this program. I'll wait here for a few seconds for you people to try out what can be the outputs of what can be the output of this program. Please, please feel free to unmute yourself and discuss, or you can also type your answers in the chat and can discuss. So here we are calling a parent kernel with 10 threads. I mean, they are warp threads, and if thread id x.x, I mean, within the parent kernel, if the thread id x.x mode 2 is 0, please note that k is defined, hash defined as 2. Thread id x.x mode 2 is 0. We are calling some child kernel with 2 threads, and we are passing this thread id, and then we are printing something, and inside this child kernel, what we are doing is we are printing some number based on the ID of father and the current ID of the thread. So please think about it and post your answers in the chat, and probably then we will discuss about it. Okay, okay, I'll probably wait for a few minutes. Please try out and post your answers in the chat. That is, if there is some response. Gokul is saying ignoring the printed in if 1, 2, 3 up to 9. Okay, I think this is correct up to some extent, but yeah, I mean, you
Sir,
should
0 to 9.
Yeah, that is correct, 0 to 9, but why are you ignoring this if is the question. Okay, so let us understand this. So I think you're probably getting this thing, but partially I would say. So there is some point that is still missing. So okay, let us understand this. So this can be the output of this program. So this is one possible output. There can be multiple possible outputs, and we'll see them. So okay, let us try to understand it step by step. So there is this parent launch here. That is, we are launching the kernel from CPU with 10 threads. Now, based on the thread ID, that is, if it is an even thread, that is, we are doing k mod 2, right? If it is 0, that is, we are checking if it's an even thread. That is for thread with ID 2, 4, 6, and 8 will go, sorry, 0, 2, 4, 6, and 8 will go inside this if condition. And what we'll do is we'll launch this kernel. And what we are doing is we are passing thread ID. So for thread 0, thread ID will be 0. So father value will be 0. And 0 plus 0 is 0, and 0 plus 1 is 1. So please note that we are launching 2 threads, and hence this thread ID will be 0 and 1 for each of the launch. And this value of father might vary. It will be 0, 2, 4, 6, and 8. So based on that, the values that will be printed will be 0, 1, 2, 3, 4, 5, 6, 7, and 0, 1, 2, 3, 4, 5, 6, 7, and 8, 9. So I hope you are getting it. For the first launch of this child kernel, so please note that there will be 5 launches. For first launch, father is 0, and since father is 0, 0 plus 0 is 0, and 0 plus 1 is 1. So this is by the first, not first launch, but the launch by the thread with thread ID 0. For the launch done by the thread with thread ID 2, it will be 2 plus 0 and 2 plus 1. So 2 and 3 will be printed. For the launch with, for the launch by the thread having thread ID 4, it will be 4 plus 0 and 4 plus 1, which is 4 and 5, and so on. For the threads with ID 6 and 8. So we'll get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is fine. But something else is also there, right? After launches are being made, we are printing here something. And what we are printing? Called child with starting %d. So essentially we are printing the thread IDs, right? But we are also printing this some string here. So, and for which threads it will be printed, which will enter inside this if condition, and which threads will enter inside this if condition. Those are the threads 0, 2, 4, 6, and 8. So called children with starting 0, 2, 4, 6, and 8 will be printed. So I hope that this is clear, and this is one of the possible output. So now my question is simple: can this entire bunch of statement, which is called with called children with starting 0 and 2 and 4, this I'm calling this entire 5 statement as some bunch of statement. Can this thing happen? So considering that this is a bunch of statement, can this type of output be possible? 0 is printed, 1 is printed, 2 is printed, 3 is printed, then this bunch of statements is printed, and then this 4, 5, and so on is printed till 9. Is this output possible? This type of output? Okay, there is some response already. Rishikesh is saying yes. Would you like to explain why you're saying yes?
Yes, sir. Like as you said in the previous example, also like if like the warp threads, there cannot be any jumbling. But like when 0, 1, 2, 3 are over, like that bunch can appear, and then the other warps can appear.
Okay, I was unable to understand it completely, but yeah, let us understand why that is possible. So okay, so why this can happen is that this kernel launch here is asynchronous. So this 10 threads, this parent kernel is being launched, but it's being launched with 10 threads, and 5 threads are entering this if conditions, if condition, and they are launching the kernel and they are moving on. So all these 5 threads which are launching this kernel, they won't wait at this kernel to finish. They won't wait for this child kernel to finish and then only they'll proceed to next statement. That will not happen. They'll launch the kernel and then they'll move on to the next statement. So please note that the SIMD execution is still there. So they'll execute this statement and then move to this statement. But the point that I'm trying to highlight here is that it will not happen that they'll finish this statement, then wait for this child kernel to finish and then only proceed to this next statement. That will not happen. So they can launch the kernel and then move on. So if that is the case, what can happen is they can launch the kernel, and meanwhile this kernel child can print some of the values, which can be 0, 1, 2, 3, and meanwhile that printing is happening, the 5 threads which have entered inside this if condition might print this printf. So it might happen that this bunch of statement which I was telling can appear at the beginning, or can appear after this 0, 1, 2, 3, or can even appear at the end after all this 0, 1, 2, 9 is printed. 0, 1, 2, 3 up to 9 is printed. So I hope you are getting the crux of it, that this as we have in CPU, that the kernel is being launched and then CPU moves on. In the similar way, on the GPU, threads will launch the kernel and then they'll move on. They will not wait for the child kernels to finish. They'll move on and execute the print statements that are after it. And due to this asynchronous kind of execution between parent and the child kernel, there can be any jumbling that can be possible between this statement, this bunch of statements, and this 0 to 9. I hope that you are getting you are getting the concept, or the point that I was trying to highlight. There is some question. It shouldn't be possible because we have threads, but maybe if a kernel ends really faster than the other. Okay, I am unable to understand this question. It shouldn't be possible because warp threads, but maybe if a kernel ends really faster, then the other. Upul, can you unmute yourself and tell what were you trying to? So I hope you are getting that this launch. I mean, they parent threads won't wait at this launch. They'll just launch it and then they'll move on, and hence there can be jumbling. If I am probably not able to. Okay, okay, I understood. So you are trying to understand why it is happening. Okay, that's fine. Your second question is, sir, then is it likely, then is it like heavy divergence? In what context you are telling this heavy divergence? Can you elaborate for this heavy divergence? Why you are telling that there is heavy divergence? Yeah, I think okay, if you have any questions, then you can unmute yourself and ask. I'll move ahead from here. Okay, so let us brief out the computation and memory related aspects of the dynamic parallelism. So parent kernel is associated with a parent grid. We know that this when we launch a kernel from a CPU, it's associated with some grid. In the similar manner, child kernels are also associated with a child grid. In the similar manner, as we have this grid associated with the parent, we have also grid associated with the childs. And the point here to note is that one parent grid or one parent kernel can have multiple child grids associated with it. Because we are launching, each thread of a kernel is launching each thread of a kernel is launching another kernel. Hence, for a particular parent kernel, there can be multiple child grids associated with it. So I hope you are getting it. So if you're launching a kernel with n threads, and each thread of that kernel is launching another kernel within it with n threads, then in this case, with the with one parent kernel, there are n child grids associated. So I hope you are getting this point. And then, as I mentioned in the previous example, that parent and child kernels may execute asynchronously. So here, child kernel, which is being called here, and the threads of the parent kernel are executing asynchronously. And if you want to synchronize them, you need to add CUDA device synchronize as we do in CPU. You need to add you need to add this CDS here. And yeah, this point is important. A parent grid is not complete unless all its children have completed. So yeah, this point, what it is trying to suggest us is that parent threads and child threads can execute simultaneously, but one thing that you should observe is that the parent threads will execute statements that are after this launch, right? So they can execute those statements, but the parent kernel will only end after all the child kernels are finished. So here in this case, this printfs can be printed by the parent threads, but the parent kernel here, which is ending here, will not finish until all the child kernels are over. So I hope that you are getting this point, that parent grid is not complete unless all its children have completed. Okay, so let us come to the memory aspects of this dynamic parallelism. So for the this parent and child kernels, they have this same. This parent and child kernels share same constant and global memory. That is, they have common global and constant memory. So if you want to have some information which is common between the parent and child kernel, so let us say you have to, you need some variable which is common between parent and child kernel, then in that case you must allocate that variable on the global memory using CUDA malloc. So it will be, if that is the case, then both parent and child kernel will be able to see the copy of it. But there is one thing here, that parent and child kernel will have different local and shared memories. So what this statement is trying to say is that let us say you have declared a shared array in the parent kernel. Okay, so you have a shared array in the parent kernel, and you are passing that shared pointer to that shared array inside some child kernel. So please note that it is declared on the parent kernel, that shared array is declared on the parent kernel, and you are passing its address to the child kernel. And if child kernel tries to access that shared array, then it might be, it might cause issues, right? It might cause segmentation fault or something like that, because its child kernels and the parent kernels have different shared memories. So yeah, please note that please note these 2 points properly, that they have common global and constant memory but different local and shared memories. So this will help us in determining how to do processing when we are using dynamic parallelism, especially memory related memory related processing and so on. So yeah, so next 2 points are about, yeah, so what next point says is that all global memory operations in the parent before the child's launch are visible to the child. So whatever operations are being done by parent before the launch of the child kernel are visible to the child threads of the child kernel. So in this case, let us say that before the launch of this child kernel, there were some statements or some memory operations being done by the parent kernel. And in that case, all the operations that are being done by the parent kernel will be visible to the child threads when the child call is made. So think of it like a thread fence. So thread fence is being executed before the child kernel is being called. So I hope that this point is clear. And the next point says that all global memory operations of the child are visible to the parent after the parent synchronizes on the child's completion. So whatever operation the child kernel is doing, it will be visible to the parent kernel only after the parent synchronizes on the child completion. That is, if there is some sort of a CUDA device synchronized, which is a synchronization construct, if we are doing that, then what will happen is whatever memory operations that are being done by the child, child threads inside the child kernel will be visible to the parent kernel. So let us say after this child call we have CDS and then we are doing some memory operations, then whatever operations are done here, whatever memory operations are done in the child kernel will be visible in those next statements after CDS. So I hope that these 4 points are clear. Any questions up to this point? There is some question because the printed may happen when other warp threads is still in the print may happen when other warp threads is still in the, okay, yeah, prints can happen in any order. So yeah, that is why we have this arbitrary jumbling in that example. So I hope that example was clear. In case you have any questions further on that one, then please feel free to ask. In fact, if you people have any questions up till this point, then please feel free to ask till this slide. I'll probably wait here for 2 seconds and then we'll move further to the multi-GPU processing. Okay, any questions up till this point on the dynamic parallelism part? Okay, if that is the, if you have no questions, then let's move further. Okay, so let us now discuss multi-GPU processing. So first of all, why do we need multi-GPU processing? Because answer to it is quite trivial, that if we use multiple GPUs, then we'll have more number of cores, and since we have more number of cores, we can accelerate our computation further, as well as since we have multiple GPUs, we'll have more memory also, right? So when we put all the GPUs together, we'll have let's say we have 4 GPUs, then and each GPU have some 16 GBs of memory, then we have 16 into 4, which is 64 GB of memory, right? So that is an added advantage, that we have more memory as well as more computation, so we can scale our algorithms for larger inputs. I mean, not scale, but run our algorithms for the larger inputs. So yeah, that is one definite advantage of having multi-GPU processing. And one point that you should note for this multi-GPU processing is that uh, we might be able to do multiple GPU handshakes between. We might be able to do multiple CPU GPU handshakes when we have multiple GPUs. And but the question is, will it suffice? I mean, doing multiple CPU GPU handshakes will suffice when we are. I mean, we are trying to transfer data from CPU to GPU. So, okay, so I hope that you are understanding this point. That is, when we have multiple GPUs, we need to do multiple CPU GPU handshakes. That is, since each GPU will need some data to process, we need to do data transfer from CPU to GPU, right? So we need to do some CPU GPU handshake. And the question here is that, will it suffice? So the thing is that CPU is CPU works serially, right? So we need to transfer data to GPU 0, GPU 1, GPU 2, GPU 3 serially, and this might this might create a bottleneck. So we need to use some parallel CPU library like OpenMP or something to parallelize the data transfer between CPU and GPU. So we might use multiple threads to transfer data from CPU to GPU 0, GPU 1, and so on. So yeah, we need to take care of this multiple CPU GPU handshake, and for that we might need to use parallel threads at the CPU level itself. Okay, so I hope that is clear. And this is a typical diagram. I mean, or a typical CPU GPU kind of. This is a typical diagram showing the CPU GPU architecture or multi-GPU architecture. So we have this central CPU, and it is connected here with 4 GPUs. And the point here to observe is that when we have this kind of architecture, or when we have this kind of setup, what we might need to do is, we might need to transfer some data from GPU 0 to GPU 1, or GPU 0 to GPU 3, and so on. And for doing that, it might be easy if we can do it directly from GPU 0 to GPU 1. But that functionality might not be available all the time. So if you see here, this GPU 0 and GPU 1 are placed inside this yellow box. So we can say that this GPU 0 and GPU 1 are having peer access. So that is, they can access each other's memory directly without contacting CPU. But that is not the case for GPU 0 and GPU 2. So if they want to they want to communicate some information with each other via, if they want to communicate some information with each other, then they have to do via CPU. So GPU 0 will transfer data to CPU, and then CPU will transfer to GPU 2. So yeah, so that is one point. So data transfer can be done across GPU in 2 ways. One is that using peer access, that is directly from one GPU to another GPU, and another way is via CPU. And this second way is slightly costlier than first way, because there are two steps involved, right? From GPU to CPU, and then CPU to GPU. Okay, so I hope this one is clear. This diagram is clear. Now let us move further. So in general, a CPU may have different types of devices, that is with different compute capabilities. So you might have a CPU which is attached with multiple different which is attached with GPU having multiple different compute capabilities. So your CPU might be attached with one Kepler GPU, one Volta GPU, one Ampere GPU, and so on. And that is perfectly fine. You will be able to program all of them, and without any issues actually. So yeah, and the one point that you should observe here, note here, is that all the GPUs which are attached with your CPU are nicely numbered from 0 to n. So let's say if you have 4 GPUs, then they'll be numbered from 0 to 3. And yeah, and the standard function, or the standard API to set a particular device is this CUDA set device. So whenever you do this, and I mean all the statements that comes after this CUDA set device I. So please note that this I is the device number. So let us say that you are having 4 GPUs from 0 to 3, I mean which were numbered from 0 to 3, and if you do this CUDA set device of 1, so you are doing CUDA set device 1, so you are setting device, I mean you are set, in some sense you are setting GPU 1 as my current GPU on which I would like to perform the processing. So all the statements that will come after this CUDA set device 1, I mean this CUDA set device statement will be executed on the GPU 1. I mean not all the statements, but the statements related to the GPU. So let us clarify this with example. So please note that this there is here this CUDA set device. So I am setting my device as GPU 0. Then comes this kernel launch. Now since I have set the device as 0, I'm setting the device as 0. So my current GPU is the GPU 0. So next statement that comes after it is kernel launch. So this kernel launch will now go to GPU 0. Since I have multiple GPU, I have to set this. I have to do this CUDA set device, and by doing that, what it ensures is that this kernel, this kernel will now be executed on the GPU 0, and this data copying using CUDA mem copy will also happen across CPU and GPU 0. Now in similar manner, what we can do is we can set device CUDA set device as 1. That is, I am marking now GPU 1 as my current GPU, and then I'm doing kernel launch. So this kernel K2 will now go, will now push to the GPU 1. Please note that this kernel K1 was pushed to GPU 0. K2 is now pushed to GPU 1. And then we are again doing CUDA mem copy, that is copying data from GPU 1 and CPU. So I hope that is clear, that based on this CUDA set device, whatever are the next statement after it, they'll be pushed to the appropriate GPU. If they are associated with GPU in some sense, then okay. So there is something wrong with this code from the parallelization perspective, and I want you people to think about what is something that is wrong with this code. I'll probably go to the chat so that Gokul is saying, oh, is this why we need device to device mem copy? I'm not sure about it, but I think this device to device is about copying from device to device, I guess. But I haven't used this thing much, so I'm not 100% sure about it. But I think it's related to this multi-GPU thing only, device to device. Yeah, but I need to check this one. Okay, any suggestions about this thing? This that what is wrong with this code from parallelization perspective? Any suggestions? Okay. Okay, so there is some, let us understand what is wrong. So since this CUDA mem copy is blocking, we know that this CUDA mem copy is blocking, right? So since this CUDA mem copy is blocking, what will happen is this kernel launch, this K1 kernel will be launched, will be executed on GPU, and it will, CPU will move on, right? But it will wait at this CUDA mem copy. It won't be able to go further to this next statement CUDA set device 1 and launch will be able to launch K2. So the issue here is that because of this CUDA mem copy, what will happen is that K1 will be launched, then only K2 can launch. K2 can be launched. So this execution of K1 and K2 will be serialized. And if this execution is getting serialized, what is the use of having multiple GPUs, right? If we are executing them one after the another only, then what is the use of the multiple GPUs? So in order to make sure that this K1 and K2 can be launched simultaneously, we need to replace this CUDA mem copy by CUDA mem copy async. That is, this kernel launch will happen. That is, this K1 will be executed on GPU 0. Meanwhile, CUDA mem copy is also happening. CPU will move further. It will then go to this statement. It will set the device to 1, and then it will launch the kernel K2. So now please note that kernel K1 is being launched, is being executed on GPU 0. Kernel K2 is being now executed on GPU 1, and these two things are happening simultaneously because of this non-blocking nature of CUDA mem copy async. So CPU can move on, and it will launch kernel K1 and K2, one after the another, but the execution can happen simultaneously. So K1 is executing on GPU 0 and K2 is executing on GPU 1 at the same time. So I hope that is clear, that we need to replace this mem copy by mem copy async to make it non-blocking. Okay, so let us move further. So yes, so let us come to some APIs that are available for multi-Chipu processing. So CUDA get device count will give the number of devices that you have on your current machine, and this and C is some variable, and we are passing address of that variable. And what it will do is, this API will give the it will place that place the number of device that you are having on your current machine in this variable C. In the similar manner, we are having this CUDA device can access peer API, which says that it checks whether it checks whether you can access GPU from to GPU 2. That is, this from and to are two numbers. It's not that this GPUs are indexed by the number. So as I have mentioned here, each and every GPU is numbered from 0 to n-1. So this from and to are just numbers. So let us take an example. So CUDA device can access peer, and then there is some boolean variable, and we are passing the address of that boolean variable can. So and can, and then for from and to, we want to check if from device 1 we can access device 2. So here we'll place 1 and here we'll place 2. And if this is possible, if we can access device 2 from device 1, then this can variable will be set to true by this CUDA device can access peer API. And yeah, so that is it. And this thing, this API checks can from device access to device. That is what we want. That is what it will indicate in this can variable. And if the if the access is possible, if the peer access is possible, then we need to enable this peer access using some API called as CUDA device enable peer access. And then again it's same, it has some variable peer and then from and to. And yeah, so one point that you should note here is that at hardware level, this relation, that is from and to, are symmetric. So if you can access device 2 from device 1, then it also means that you can access device 1 from device 2. And yeah, so that is clear from hardware level, but from programming level, there is asymmetry, right? Here we are what we are assuming is that from and to are from and to is different, and to and from is different. So if you want to check if you can access device 1 from device 2, then you should place 2 here and 1 here and check what is the value of can. But since at the hardware level there is symmetry, you can assume that that will be also true if you can access vice versa, right? So I hope that point is clear, that at hardware level there is symmetry, but at software level there is asymmetry enforced by this APIs. Yeah, so yeah, that is one point. And next point is that maximum 8 peer connections can have, a device can have maximum of 8 peer connections. So a particular GPU can be connected with 8 other GPUs, and yeah, you will need 64-bit applications for it. Yeah, I hope that this slide is clear and this APIs are clear. Probably we'll move to the next slide if you have any questions here. Okay, there is some question. Sir, is it clear to avoid non-blocking on GPU perspective? How to achieve non-blocking in multi-core CPU calling GPU? Okay, okay, this part I'm not sure about, how to avoid. Okay, when you are talking about multi-core CPU, I'm assuming that you are using some P threads or OpenMP, and I'm not sure if in that case there is some notion of blocking or non-blocking or not. So I'm not sure if when one thread is launching some particular kernel, let's say you are having OpenMP code which is running main, and inside that you are having kernel launch, and I'm not sure if after the kernel launch that particular thread will wait or not. I mean, so that part I'm not really sure about, but I need to check this part. Okay, so yeah, I'll say that I'm not clear. I mean, I'm not really sure about, because I have not tried this thing. Yeah, so let us move further. Yeah, so first of all, let us see this small example related to this printing the, I mean, enumerating each and every device that you have on a particular machine. So here we'll use the APIs that we learned. So we have this variable device count, and we are counting the number of devices that we have in current machine using this yeah, this CUDA get device count API, and we are passing this device count. So inside this device count, we'll get the number of device that we have, and then we are using this variable device and as a looping variable, and then we are looping it for the number of device that we have on our machine. So from 0 to device count, we are looping, and what we are doing is we are using, I mean, we are declaring a variable of type CUDA device prop, which is nothing but a structure. And once we have declared the variable of that structure type, we are passing it to this CUDA get device properties, and we are passing device number to it. So for this device number, we are interested in getting all the properties of it, and then we are printing some properties related to this device, like device number we already know, because yeah, device number we already know, and we are printing some properties related to it, like its major number and minor number, which are stored in this device prop variable, which is of CUDA device prop type. Okay, so any questions up till this point? Else we'll move to the warp voting. Quickly we'll finish that. Yeah, so I think that there are questions, and yeah, for this question we need to definitely check if how the CPU threads work internally, like are they blocking or non-blocking. As far as I know, like in OpenMP there is no notion of I mean, like SIMD execution or so. So I am assuming that you will be able to do multiple copying simultaneously without any issues. But yeah, I mean, someone should check this thing, that whether we are able to do it smoothly or not. Anyways, let us move further with warp voting. So okay, so sometimes we might be interested in doing some operations, like okay, so sometimes we might be interested in doing the operations where we need the entire walk to operate on a particular data item. So let us say that we are doing some graph computation. I mean, we are running some graph algorithm, and the operation that we are doing is like we want, for each node of that graph, we want to traverse. I mean, we want to count its neighbor, or some we want to go through all its edges. Now, the number of edges that a particular node might have varies, right? It varies greatly. Like for some nodes, they might have large number of neighbors. Let's say 1024 or 2048 neighbors they might have. And for some nodes of the graph, they might have just 2 or 3 neighbors. In that case, for a node having large number of neighbors, it might be good to assign an entire walk to it rather than assigning a single thread to it. And whenever we are assigning the entire walk to a particular data item, we might be interested in knowing some properties or some conditions related to it, related to that walk, and that is where this walk voting comes into the picture. So there are this functions like underscore underscore all underscore underscore any and underscore underscore ballot, which are used for checking a particular predicate. I mean, which are used for checking if a particular predicate or a particular condition is true or not for a particular warp. So this underscore underscore and underscore underscore all function will check if all the warp threads satisfy a particular predicate or not. So this predicate is like a condition, and what this underscore underscore all does is it check if this condition is true for all the warp threads or not. And if it is true, then it will return some value. That is, I mean, if it is true, then it will return true for all the warp threads. And then there is this underscore underscore any, which check if this predicate is true for any of the warp threads. And if any of the warp threads satisfies this predicate, then it will return true for all the warp threads. And then there is this underscore underscore ballot, and what it what it does is it checks if this predicate is true for, so this underscore underscore ballot checks if how many, which warp threads, not how many, which warp threads satisfy this predicate. So based on the threads which are satisfying this predicate, it will return some return value. We'll see how to, what it will return and so on in the upcoming slides. And yeah, this actually this ballot is just a generalization of all and any. Okay, so let us see these things with the example. So yeah, so this is our CUDA program. We are launching it with 4 warps actually. 1028 is, I think, 4 warps, right? 32, 64, 96 and 128. Yeah, so 4 warps. Yeah, we are launching this kernel with 4 warps, and then we are having CUDA device synchronize. And inside a kernel, what we are doing, we are using this all predicate, and we are checking if thread ID x.x is less than 100 or not. If that is the case, for which warp this condition is satisfied, then we want to check this. And please note that we are using this underscore underscore all function. And if all the threads of the warp are satisfying this condition, then the return value will be true. And then one of the representative of, we pick one of the thread as a representative of the warp, which is the first thread of each warp, and then we print this value of value. So request you to try out what will be the output of this program. Please type in the chat, or you can also unmute yourself and tell what will be the output of this program. Any suggestions on what will be the output of this program?
The 4 true values.
Okay, 4 true values. Someone suggested 4 true values. Okay, Gokul is saying true, 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 false. Okay, I think this is correct. Let us understand this. So for warp number 0, 1, for warp 0, 1 and 2, this is true, right? Because for this condition, this thread ID x.x is less than 100, is true for the threads from 0 to 31, which is warp number 0, 32 to 63, which is warp number 1, and 64 to 96, which is warp number 2. For all these threads, this thread ID x.x is less than 100, which is true for all the warp threads. So this all will give true for the warp 0, 1 and 2. But for the warp number 3, which contains the threads from ID 96 to 127, only first 4 threads, I guess, will have this condition as true. For rest, this condition will be false. And since that is the case, this all will return will return false for that last warp, right? Or the warp number 3, assuming that warps are from 0, starting from 0. Yeah, so the output will be 1, 1, 1 and 0, or you can also interpret as true, true, true and false. Okay, so I hope this is clear. Now I've just made a small change. I have replaced this all with any. Now what will be the output of this program? Quickly, it would be very fast now for you people. Very easy for you people now. Yes, so yeah, as Gokul is pointing out, it's all true now. Yeah, so let us quickly see this thing also. So since now for the last, so okay, so for first three warps it is definitely true, right? But for the last warp now, since first four threads of that last warp are now satisfying that condition, and since we have any, so since any of the thread of that last warp is satisfying this condition, the final output that will be stored in val will be 1. So the last warp will, so the final output will be 1 even for the last warp. So I hope you are getting it. For the previous case it was all, and hence it was 0, but now since it is any, it is 1 now, because at least one thread of that last warp is satisfying this condition, and hence it's 1. So all truths, that is correct. Now let us come to this ballot thing. So what this ballot thing suggests is, this ballot function suggests is, it tries to it tells us which threads of this warp satisfy this condition. So this condition, which threads of the warp are satisfying this condition, and based on the threads that are satisfying this condition, it will set the value 1 and 0. So let us understand what will happen here. So for the first warp, all the threads will satisfy this condition, right? So what this ballot will return is, it will return all ones 32 times for the first warp, and similarly for all the warps, second warp also and third warp also. So for warp 2 and 3 also, this it will return 1 1 1 1 1 32 times. And for the last warp, what will happen? So I'm talking about last warp now. For last warp, what will happen is, since only first 4 threads of that last warp satisfy that condition, so it will return 1 1 1, and for rest all bits it will be 0, right? So last 4 are ones, last 4 bits are ones, 1, and rest all the MSB bits are 0 for the last warp. Now it won't print this thing, it will print the hexadecimal format for this. So hexadecimal format for this all ones 32 times is nothing but this thing, right? F. So if you people know the hexadecimal representation, then F is nothing but F is nothing but this, right? F in hexadecimal F is nothing but this 1 1 1 1, and since each warp has 32 threads, and 32 divided by 4 is nothing but 8. So for each warp, not for each warp, but for first 3 warps, 8 Fs should be printed, right? For first 3 warps, 8 Fs should be printed, and that is what is the case, right? For first warp we have 8 Fs printed. For second warp and third warp also same, 8 Fs are printed. And for the last warp, if you see here, for last warp this was the output, right? All zeros, and then last 4 were 1 1 1 1. Last 4 bits were 1. So if you see what is the hexadecimal representation of this, it's just single F, right? Because leading zeros, leading all bits are zeros, so that won't affect the final value, and the actual number is just this last 4 bits, which are 4, right? Which are 4 ones, right? And in hexadecimal it's just an F. So for the last warp it will just print F. So I hope you are getting this, and let us move further from this. And in similar manner, if I replace this condition, here the condition was thread id x.x less than 100, but if I replace it with thread id x mod 2 equals to 0, then all odd threads will satisfy this condition. All even threads, I guess, yeah, all even threads will satisfy these conditions, and all odd threads will not satisfy this condition. So output will be something like this. For thread 0 it will be 1, for thread 1 it will be 0, for thread 2 it will be 1, for thread 3 it will be 0, and so on. This will go on. And if you see, if you find the hexadecimal representation for this pattern, it will be nothing but 5 5 5 5 5 5 5. printed 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. So this will be the output for one warp, and this output will be same for each and every warp. I mean all the 4 warps now, because here our condition is not something like this less than 100. It's this thread idx.x mod 2, and yeah. So I hope you are getting it. So you will get all fives. I mean 8 fives for each warp. 8 fives for each warp you will get, and this will be the output of this program. Any questions up till this point? Okay, Ramasamy has typed something. Okay, what I mean for what for what question are you suggesting this output, Ramasamy?
No, for that 4th warps, like all ones followed by all zeros, and the last 4 bit is 1. That's what I
Yes.
had.
Yeah, that is correct. Yeah. Gokul is saying if we have a ballot 0000100, can we assume thread IDs 3, 4, 7 are satisfying? Yes, that is precisely what will happen. So it will be go from the thread IDs will go from the least significant bit. So this last bit is for thread 0, second last bit is for thread 1, and so on. So yeah, this one is for the thread 0, 1, 2, 3. Yeah, that is correct. So 3, 4, 5, 6, 7. Yeah, that is this is correct. Yeah. So yeah, precisely this 3, 4, and 7 threads are satisfying this condition. Okay, I hope this part is clear, Gokul. If you feel I missed something, then you can unmute and ask. Okay, so let us move further from this. Let us finish our discussion with this warp voting. Okay, so we can in general combine this warp voting and atomics to efficiently do atomic operations. So let us see how to efficiently do atomic operations by using this warp voting. So let us say that you have this condition, you are doing some atomic increment. So this is an atomic increment you are doing on some variable counter based on some condition. So if this condition is satisfied, you will increment the counter by value n. And this is what we want to do. And what will happen is this will be executed by many of the warp threads, right? Assuming that this condition is true for many of the warp threads, this atomic increment will be executed by many of the warp threads, but not all. Let us say out of 32 warp threads, 20 were having this condition true. So 20 threads were doing atomic increment, and rest threads were not doing anything. But yeah, 20 threads were incrementing it. So the problem with this type of approach is, this type of code is that it has high contention. That is 20 atomic calls are being made, right? And that is quite costly. Let us say that 20 threads, 20 warp threads were satisfying this, and 20 times atomics is being called, and hence there is high contention. But we can optimize this thing by using ballot, and let us see how to do that. So for doing that, what we'll do is we'll choose one thread as a leader thread, and we'll collect the warp count by using ballot. So we know that ballot gives us the mask, or right? So we have seen this, right? The ballot gives some indication that which thread is satisfying a particular condition. So we'll calculate a mask based on some condition, and after calculating that mask, we'll set how many bits are set. How many bits are set in that mask by using some Proxy function. So Proxy and then providing some mask to it will return the number of set bits inside this mask. And yeah, so these two functions will be used to implement this this statement efficiently, and we'll see that in next slide. And apart from these two functions, there is this underscore FFS function, which takes mask and returns the first set bit. So if let's say the first set bit from the LSP. So from LSP, let's say that third bit was the first set bit, then it will return 3. And yeah, and how we'll do that atomic? This statement. How will we optimize this statement? Is that only leader will perform a single atomic add, and that will reduce the contention. That is, we are not doing atomics. We are not calling atomic function 20 times. We are just calling it once, and that call will be done by the leader. Now let us see how that is being done. So that this was the original code that we wanted to optimize. Now we want to optimize this using ballot and POPC that we saw in the previous slide. How can we optimize it? So this condition, instead of doing this thing, what we'll do is we'll write this condition in ballot. And what will this thing do is it will give us the number of threads that are satisfying these conditions. So we'll get we'll get the mask based on it, right? So let's say 20 threads were satisfying that condition. Then in this mask, the 20 bits will be set to 1 and rest all 12 bits will be set to 0. So this mask will be having interleaving of 1010 and 20 ones will be there and 12 zeros will be there. Now we are taking we are picking up one thread, which is thread 0 as the leader. So thread id x.x mode 32 is 0. We'll pick up 0th thread of warp 0 as leader, 32th thread of warp 1 as leader, and so on. So we are taking one thread from each warp as a leader, and what that thread is doing is that it is just doing one atomic now. Please note that, it will that leader thread will take a lead of adding that final value in the counter, and the way it will add that value in counter is that it will count the number of set bits in this mask. So by using this POPC function, it will come to know that okay, 20 threads were the threads which were satisfying this condition, which was this. So 20 threads were satisfying this condition, and since only 20 threads are satisfying the condition, I only need to do 20 times this add. I only need to add 20 number to this counter, and that I can do just by doing one atomic add. So I hope you are getting this. Initially, the 20 threads were satisfying this condition, and this atomic increment was being called 20 times. But now, only just one atomic call is being made, and that is using this. That is using this. And how we are counting this? The threads which are satisfying this condition using ballot and POPC. And I hope that this is clear that here 20 atomic calls were being made, and here just one atomic call is being made, and that too by the one leader thread that is that we are picking from each one. Any questions up to this point? So this is the more optimized code. I hope you are getting this. Here only one atomic call is being made by one leader, and here the number of atomic calls that will be made will depend upon how many threads satisfy this condition. It can be 1, it can be 0, or it can be even 32 in worst case. Okay, any questions up till this point? Could you explain how one atomic call again? Could you explain how one atomic call again, and the POPC also explain once more? I don't understand this part. How one atomic call again? Okay, I'll explain this POPC part. And there is the other question also. Can we use multiple masks? Okay, okay. Let us come to this question also. Okay, so so this POPC function is nothing but it counts the set bit inside this mask. So what this ballot does is it based on this condition, it will set the bits. Set the 32 bits, right? So let's say we have 32 threads. 32 warp threads, and based on whether this condition is being satisfied is being satisfied by a particular warp thread or not, it will set those bits inside that 32 bit. It will set the bit inside that 32 bit binary number, right? And that entire thing forms a mask. And what POPC does is it just counts the number of set bits inside that mask. So I hope that part is clear. That question by Gokul is clear. And can we use multiple masks? Okay, this POPC will take only just one mask, but you can definitely find the multiple masks, right? So what you can do is you use ballot multiple number of types and multiple number of times, and you can just keep on finding different types of masks based on the different types of conditions. So I hope that you are, I'm able to properly point out your question, but if you feel that I missed something in your question, then please do let me know.
Yeah, that's fine, sir. Actually, I was worrying for one condition, how we can use multiple masks. I have only one condition to be satisfied, but then I want to use different mask sets. Is it possible? I was wondering, just a vague question might be.
Okay, you have just one condition and you want different mask. I don't think that will be possible, because a mask can be unique based on a particular condition, right? Because if you see, there is one-to-one mapping between condition and mask.
Yeah, in some cases, I want to toggle between the two masks for the same conditions.
I'm not sure how to do that, but currently what's going on in my mind is like, since you are not modifying a condition, you will be mapped with the same mask, whatever the case might be. But coming to your question, that toggling the mask based on something, I think you need to tweak this code a bit. You need to think about it. How can you keep the conditions same and keep on changing the mask? So you can, once you calculate the mask, you can probably do some operation on masks to change the value of it based on what your requirement is.
Okay, sir, got it.
How we can have only one atomic call in the optimized code. Okay, let us come to this thing. Okay, so see, initially based on what condition was, how many warp threads were satisfying this condition, that many atomic calls were being made, right? So let's say out of 32 warp threads, 20 were satisfying the condition, then there were 20 atomic increments, right? But here, since we are first of all calculating the mask, right? So this condition is same here and here. Please note that this condition and this condition is same, and this condition being satisfied by, whatever threads are satisfying this condition, we are calculating we are setting the bits for those threads as 1, and that information is stored in mask, right? Now we are only taking one thread here. Out of all the warp threads, we are only just picking one thread as representative out of all the warp threads. And then based on the number of increments, based on the number of set bits in the mask, we are, which we can calculate using Proxy, we are incrementing the counter. So I hope you are getting it. Here only, one increment is for the warp threads. So here 20 warp threads were doing atomic increment. Here only one warp thread, that is leader that we pick, is doing the atomic operation, that is atomic add. So we have reduced the number of atomics that are being, called to the atomics that are being done. So I hope you are getting what I'm trying to say. Okay, I'll come back to the questions later. Just let me finish this. Okay, so I think now it will be very simple for this. This code is very simple, right? We are launching a kernel with 4 watts, that is 1028 threads, and we are using palette here, and again we are checking that standard condition, if thread ID x.x is less than 100 or not, and we are storing the final mask in this unsigned integer val, and one representative of the mask is one representative, meaning here we are choosing the first thread of the every warp as the representative. So 0th thread of the warp 0, 32th thread of the warp 1, 64th thread of the warp 2, and so on, will print the value. And since we have 4 warps, the 4 values will be printed here. And what Proxy is printing? The number of set bits, and the number of set bits here for the warp 1 will be 32, right? Because all the 32 threads of the warp 1 will satisfy this condition. Similarly for warp 2 and warp 3, but for warp 4 only 4 threads will satisfy the condition. Hence the output will be 32, 32, 32 and 4. So I hope you are getting this. So yeah, let us finish this with the last slide for the today. And yeah, so this slide has some point that I want to derive. So if a warp quoting function is used is executed within a condition, so here warp quoting function is which is palette and popc are executed within condition. Some threads will be masked, so they here in this case even threads will enter or odd threads will be masked and they would not participate in voting. So here only out of 32 threads of the warp, only 16 threads will enter, right? Because we have this condition, right? So out of 32 threads of a warp, out of those 4 warps, I mean we were having 4 warps and each having 32 threads. So for each warp only 16 threads will enter, and similar, I mean as we saw in the previous example, all the threads of first warp satisfy this condition, and same is true for second and third warp, but for the fourth warp only 4 threads satisfy the condition. And since now half of the threads are only entering, the number of set bits will also be half. So initially it was 32 and 4 here. Now it will be 16 and 2. I hope you are getting this, since only half of the threads are entering. Here all the threads were entering, but here we are, I mean, reducing the number to half, I mean based on if it is a even thread or odd thread, and based on that we are printing this number of bits that are set by the ballot function, and we are counting this number of set bits using popc, and then we are printing it, and the numbers will be 16 and 2. Okay, so any questions up till this point? I'll be there here for a few more minutes. I'll take all of your questions, and yeah, so let us come to the questions. I think I answered this question, how we have only one atomic call in optimized code. If there was any, I mean, if something was unclear, then please feel free to ask. Sir, in this code we have n set bits. We are adding n to counter for every even thread, right? Which code you are talking about, Gokul?
Sorry, sir. That one I figured out, sir. I made a mistake.
Okay, that's fine. Okay, let us come to next question. Okay, that's fine. So is there any way to get, is there any way to set the arch SM_35 RDC plugin collab? Okay, I'm not sure about the collab, but yeah, I need to check this out if we can set this thing or not. So coming to this part, this dynamic parallelism, I haven't tried on collab, but on the Linux machine, I mean, in the case that you are having GPU on your system itself, then it will smoothly work by specifying this thing itself, right? Sorry. Yeah, if you are having GPU installed on your system, then just doing this thing will work. But I'm not sure about that collab thing, and I need to check that out. Okay, so this part I'll probably look into it and will post into that Google group.